the May meeting of the Shasta Stargazers. So, do we have anybody on Zoom, Jim?
Yeah, somebody just.
Okay, can they hear me okay?
Yes, I can.
Yeah, can you hear me okay? Okay. Okay, well, let me,
Well, John, can I first say thank you for the emails and the attention?
oh, no, you're
Appreciate
quite
it.
welcome. Yeah, I'm glad everybody's getting them okay. Yeah. So we'll keep them going, keep everybody informed. So, oh, again, welcome. So tonight. Okay, so this is what we'll be talking about tonight. We got the news and events. We'll do our what's up in May, so if you go outside and observe, you'll know what to look for. And then our own Jim Havlis will be doing a talk on the James Webb Space Telescope. And then we'll open it up to everybody to anything that you want to discuss. So first off, current events. We've been talking about this since last year, T Corona Borealis. We're still waiting for it. It's overdue from the last event back in 1946, but
Jim, I
still
can
keeping-
hear you.
Yeah.
Talk a little louder.
Okay, yeah, we're still waiting for this event to happen. It should have happened late last year, but it still hasn't happened. But one of our members, Jeff Weiss, has some sophisticated equipment and he's monitoring it. So as soon as it does go, NOVA, we'll get the word out because it'll go, quickly in a matter of hours to about magnitude 2, and then be there roughly for, I think, 4 or 5 days before it starts fading again. So we'll be sure to get the news out to everybody. But in the meantime, it might help if you know where to look so you can practice going out. Let's say tonight, even with the bright moon, you should be able to see it. So this is it here.
It's between Arcturus and Vega.
Yep. Yeah, if you remember how to all the Dipper stars, you get to Arcturus. And then if you look down to the left, you'll see Vega. So Corona Borealis is right in between there. The sky is dark enough, you should be able to see it. So when it does go nova, it's going to appear as a new star right about here. It's about the same brightness as this one here, so it should be obvious when it does occur. Now this is a once in a lifetime event, so we'll be sure to get the word out and hopefully everybody have an opportunity to observe it. Okay, and upcoming events. Now 15th of May, the Siskiyou Land Trust is doing their dark sky tour. It requires pre-registration. You have to go to the website and register for the event. And then they'll send out details about the location. It's going to be off of Highway 97 near the Big Springs turnoff. I think it's about a mile north.
9/10 of a mile
Yeah.
past it.
Yeah. So, it should be close enough that if it's clear, I think we should attempt to be there. But given the clouds last month, we weren't able to do our first star party of the year, which was a disappointment. So what I did this month was actually scheduled 2 star parties, one on the 23rd of May.
23rd?
Yeah, one on the 23rd of May, and then a backup one on the 30th of May, so a week later. Now on the 23rd, there won't be any moon in the sky when it gets dark. So if you want to look at deep sky objects immediately following sunset, then that'd be the time to go. And on the 30th of May, a week later, you're going to have the moon in the sky. It's not going to set for a while, so you have the opportunity to look at the moon if you want to do it.
Venus Sky Sanctuary is the name of.
Yeah, that's our dark sky site. That's just east of McLeod. So. And then if you want to go to more formal star parties, we got 2 of them coming up. The Oregon Star Party on 24 to 29 June. And then the Golden State Star Party, which is one I've attended in the past, and yeah, I recommend that if you have the opportunity to do it for 25 to 29 June. And this year, they're not closing the registration off, so if you decide you want to go, you should be able to register up to the last minute. And on the 4th of October, we're going to be doing our annual International Observe the Moon Night.
Mhm.
And then, of course, we're going to do our annual trip to the North Bedford High School Planetarium. I was hoping to get it scheduled in May and June, but they have, conflicting schedules, so it may be a little bit later. So by next month, I should have a date established as to when that'll be, but it will be on a Saturday. And we'll carpool like we did last year and drive up there. And then the Hat Creek Radio Observatory, they have self-guided tours on Thursdays. So we need to pick a Thursday that would work for everybody, and we can head up for that.
Hey, John?
Yeah.
The first entry, what is that?
It's just they have a star party at Siskiyou Land Trust. They have where they go under, it doesn't last very long, about an hour and a half, but they get people out. And
What is the Siskiyou Land Trust?
It's across the street from here. The
Yeah.
building right across the street.
yeah, I think they manage a lot of the areas in
Oh.
Siskiyou County, the public areas.
Huh.
And Siskiyou County.
Do they bring telescopes and all
Uh,
that? Do they-
I don't think they have telescopes that they bring, but they encourage people to bring telescopes.
okay.
But apparently they have an astronomy teacher that
Oh.
gets out there and kind of points out,
She used to be a member of this organization, Barbara Olson. I don't know if you remember her. She spoke with a little bit of an accent.
Huh.
She was a teacher for 30 years down in LA. She'd take the kids out of,
Oh, I remember.
the city and out to the desert.
yeah.
Yeah,
and Starves her.
I remember meeting her and I thought she was gonna be a regular, but I
Yeah.
hadn't seen her in a long time.
Right. She's doing her own thing.
Oh, okay.
Yeah.
Okay.
And we're invited to participate.
Huh.
Yeah, and
Okay.
I'm hoping to make it on the 15th, so hopefully we'll see you there. Okay, and here's some of the specifics for the May star parties. You get moonset well before dark, well before sunset. And civil twilight ends at 9 p.m. and nautical twilight at 9:41 p.m. So it's gonna be a while to get really dark. So we'll probably, if you have telescopes that you want to set up, probably recommend getting there around 8 o'clock. Otherwise, I think getting around 9:30 would be a good time on both of these.
Just asking your wife if she wanted to sit down.
So. And then the backup would be a week later. Where, sunsets are approximately the same, it's a little bit later each time. But then the moon doesn't set until, after midnight, so you won't have truly dark skies until after midnight. Okay, before we get into Jim's program, there's something else I want to mention. I'm gonna formally go out with an email tomorrow, but we've been invited to give a presentation to the Liberty Arts Gallery in Wairika. They put on a program every once in a while where they invite groups of about a dozen people to give a 6-minute presentation on things that they're doing. So what I wanted to do is get our club members to submit photographs that they'd like to share with the audience and kind of tell them about what the Mount Shasta Stargazers are all about. So like I said, I'll come out with an email tomorrow with more details, but I think it's a good opportunity to reach out to our local community and let them know who we are and what we do.
I was talking to a guy as I was coming in, he said, well, the library's gonna close for these, and I said, well, there's a meeting, and we started talking, and he's asking questions about the planets, and I'm just talking with him, he was like, wow, and it was like. Yeah, he was interested, he knew nothing about the meeting, not
Okay.
much about astronomy.
Yeah, I've seen a few people, on the way out that, seem like they're interested, but they never come back.
So, oh, well, any idea when this thing in Eureka might happen?
Yeah. Yeah, it's gonna be. No, I didn't capture that on, but it's on towards the end of the month, we have to have our presentation in by the 21st. So, let me see if I can. Well, I'm on airplane mode, so I can't bring it up right now, but that'll be in the email tomorrow when I send it out. So. Okay, so without further ado, let's have Jim.
Do this thing.
Do his thing. So I think, the speaker
I thought it
in
was
the
really
camera,
good.
if you stay close to the other people on.
Yeah,
So to advance the slide, you get here, and if you want the laser, press that one there. Just the laser? Yeah.
And then press down to go to the next one.
Yep. Okay. Thank you, John. Appreciate it. Can everybody hear me okay? Am I speaking loud enough? Great. In 1750, one of the world's greatest mathematicians sat down at his desk to analyze a problem that he knew he couldn't solve. The problem had been around for about 60 years, and others had tried to solve it, but were unsuccessful. So he looked at the problem and tried to find some simplification to the problem that might allow him to come to a solution. And after a bit of thought, he did. He found a simplification that allowed him to solve this problem. He was, of course, justifiably proud of what he had done, but he could not possibly have known that 250 years later, the solution that he came up with would be the exact solution that the designers of the James Webb Telescope would need in order to make their telescope feasible. Who was this mathematician?
What was the problem?
And what was the problem he was trying to solve? And what was the simplification that he made that allowed him to solve it? We'll get to all of that in a bit, Lily. So, but this evening I'm going to talk about the James Webb Telescope, but actually I'm not going to talk about the telescope at all. I'm not even going to show you any pictures that the Webb Telescope has taken. Rather, I'd like to show you something that's equally important, but that doesn't get very much attention. Namely, where the telescope is located in space and how it moves. And it's a tribute to the orbital scientists and the orbital engineers who have designed this system. And I think you'll find it quite amazing. But first, a little background. In the mid-1990s, astronomers and astrophysicists realized that if they really wanted to understand how the universe evolved, they would need to look at stars and galaxies that had formed very early on after the Big Bang. The Big Bang occurred about 13.8 billion years ago. And astronomers believe that the first stars started forming about 500,000 years later. So astronomers were interested in looking at objects that had formed roughly 13.3 billion years ago. And let's just round it off and just say 13 billion years. The stars that were born then had characteristics similar to stars that were born much, much later. And in particular, in the electromagnetic field, in what we call light, the spectrum was very strong in the visible light, that is visible to humans, and ultraviolet light. But in the 13 billion years that this light has been traveling through the universe itself has expanded. And so this light has been
undergone what's called the red shift. And the shift has been pretty extreme, so that what was originally visible light and ultraviolet light, now when we receive it on Earth, is approximately what's called the mid-infrared to near-infrared range. In the mid-1980s, or 1990s rather, there were no telescopes that were able to take images in that frequency range. So if they wanted to look at these objects, they were going to have to build a telescope. In fact, they were going to have to build an infrared telescope. Now, one option, of course, is to build a telescope on the Earth. But it turns out that the atmosphere of the Earth absorbs some of the infrared radiation that they wanted to observe. And so that's not a very good place to put it. So if they wanted to really observe these things, they were going to have to launch their infrared telescope into space. It's an ambitious undertaking, but fortunately, there was already a proof of concept. The Hubble telescope had been launched in 1990, and after an initial glitch, had been spectacularly successful. By the mid-1990s, the images were just amazing to see. And so the idea was pretty good. The thing about an infrared telescope that's going to be imaging things that have been traveling through space for 13 billion years is that the signal is going to be extremely weak. And so they would need a very, very sensitive telescope. In science and engineering, there's a concept called signal-to-noise ratio. You want this ratio to be as large as possible. In other words, you want as much signal as you can get with as little noise as you could possibly get. To get as much signal as they could, they designed a telescope, which is going to be very large. The telescope itself is actually about 21 feet in diameter. It's a huge telescope. And it would accumulate a lot of this infrared radiation that's coming in, but nonetheless, the signal is going to be very, very weak. And so you also have to work on the other end of it, which is to reduce the noise to an absolute minimum. Infrared radiation is really almost the same as heat. And in order to get these very weak signals, they were going to have to cool the telescope down to a very low temperature. They would like to get it below 370 degrees Fahrenheit. You can do that by placing the telescope far out into outer space. Outer space is very cold, and you can achieve that kind of temperature. In that way, the telescope itself is not radiating any significant amount of infrared radiation, and so it doesn't actually blind itself. But there are two other sources of radiation that are very strong. One comes from the sun, and the other comes from the Earth. And so they were going to have to build a shield, a sun shield, that would protect the telescope from the intense rays of the sun and whatever rays of the infrared radiation is coming from the Earth. And they figured that if they could get the telescope about 1 million miles away from Earth, they could design the heat shield so that the radiation that's impinging on it could be dissipated by the heat shield. But putting the telescope 1 million miles away from Earth presents a problem. The problem is, as we'll see in a moment, is that 1 million miles away from the Earth, the major gravitational influence on the telescope will be the sun, not the Earth. And so the telescope will actually be orbiting the sun. The Hubble telescope, which is about 350 miles above the Earth, is mostly influenced by the gravity of the Earth. So it orbits the Earth. But the telescope, 1 million miles away from Earth, is going to be its orbit is going to be dictated by the sun. And that means that the telescope is going to be following all of the laws of orbital mechanics that the planets do. The planets have where the planet's orbital laws were deduced by a fellow by the name of Johannes Kepler. And he published his results in 1619. And this is a remarkable thing that he did, because he took notebooks of just data that had been acquired by a fellow by the name of Tycho Brahe and himself. And he analyzed these numbers, just pages and pages of numbers. And he was able to deduce these three laws. I think you're probably all familiar with them, but let's go over them quickly. The first is that the orbit of every planet is an ellipse with the sun at one of its foci. I think we all knew that. The second is that the line joining a planet and the sun sweeps out equal areas at equal time, intervals of time. And the practical consequence of this is that the planet moves faster when it's close to the sun, and it moves slower when it's farther from the sun. Neither one of these has any major impact on the design of the James Webb Telescope. But the third one does. And I simplified the third law. It's actually an equation, but we only need to consider the consequences of it. And the consequence is that planets close to the sun move in their orbits more quickly than planets that are farther from the sun. And here's a couple of examples of it. Mercury is the planet closest to the sun, and it rotates about the sun in approximately 88 Earth days. Earth, which is the third planet from the sun, revolves about the sun in 365.25 days, what we call a year. Jupiter, which is much farther from the sun than the Earth, revolves about the sun in approximately 12 Earth years. So there's this progression. The farther away you get from the sun, the longer it takes for the object that's in that orbit to orbit around the sun. And that's the problem, because even though you might launch the James Webb Telescope such that there's a line of sight between the Earth and the telescope when you launch it, eventually the Earth, being the quicker of the two, will be moving around in its orbit faster than the James Webb Telescope, and it'll eventually duck behind the sun. And once you do that, you lose contact with your telescope because you can't transmit radio waves through the sun. So that's the problem that they were going to be facing. In 1687, Isaac Newton came out with his magnum work called the Principia Mathematica. And in it, he developed his theory of what we call today classical mechanics. And it included in his theory of gravitation. And his theory of gravitation was that if you have two objects of two different masses, the force between them will be proportional to the product of the two masses divided by the square of the distance between them. It was a major advancement for science. For the first time, we have an actual theory that would allow you to calculate how objects moved depending upon the forces that were impinging upon them. And in particular, in our case, where we're interested in gravitational forces, you are actually able to use the classical mechanics and the law of gravitation to actually derive the laws that Kepler had derived from just his notebooks. So this was a great advance, and it was a great impetus to scientists accepting Newton's theories. Every student of physics early in their course, in their studies, takes a course in classical mechanics. And along with it, the theory of gravitational attraction. And it's a moment, I think, of great enthusiasm for the student, because when you're presented with a student, you have a system where you can take two objects, two different masses, some distance apart, with some initial conditions, and you plug them into the classical laws that Newton had developed, and you can tell how these two objects will move relative to each other. In other words, you can calculate their orbits. It seems like a great powerful tool. Unfortunately, that enthusiasm is quickly dashed because, unfortunately, if you add one more body to that two-body problem, the problem becomes unsolvable. It turns out there are more unknowns than there are equations that will allow you to solve it. In general, for example, if you have one unknown, you need one equation to solve it. If you have two unknowns, you need two equations, and so on. With a three-body problem, you actually have many more unknowns than three, but the bottom line is you don't have enough equations to solve the problem. So this problem had existed for about 60 years. And this is where the mathematician that I mentioned at the beginning of this talk comes into play. His name was Leonhard Euler. I'm using the German pronunciation of his name. He was born in Switzerland, in the German-speaking regions of Switzerland. I'm blocking your way here. And he is considered one of the greatest mathematicians to ever have lived. And he decided he was going to look at this problem, this three-body problem, to see if he could find some way he could get some partial solution. He knew he couldn't solve it exactly. He was going to have to make some assumptions and some simplifications, but he wanted to see if he could try to do it. And as I said, he found a way to do it. For the time being, ignore these things about forces and things. I'd just like to show you exactly what he did to make the first simplification. So I'm showing the sun, the earth, and a satellite, but he actually had it more general, just any two bodies that you would like. But since we're going to be considering the sun and the earth, we'll start out with those two. His first assumption was, we'll take a line and we'll draw it from the center of the sun to the center of the earth, and we'll extend that line as far out as you need to in any direction, in those two directions. And then the simplification he was going to make is he would then place that third body, whatever the satellite or telescope would be, we'll place it along that same line so that all the forces on the satellite would be collinear, but all pulling in the same direction. So this reduced the problem from a three-dimensional problem to a two-dimensional problem. So that helped a lot. The other assumption that he made was that the satellite, or in our case, the telescope, would have a mass that's much, 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 much less than the mass of the sun or the mass of the earth. And that's certainly the case with the telescope. The James Webb Telescope weighs about 14,000 pounds. It's very heavy from any human perspective, but compared to the mass of the earth or the mass of the sun, it's minuscule. And so the James Webb Telescope meets that criterion. So with these assumptions, he was actually able to come to a solution. The solution was actually quite complicated still. It resulted in what's called a quintic equation. A quintic equation is one in which some of the variables are raised to the fifth power. So you're going to need some pretty good mathematical prowess to be able to solve this. But this was well within his range of mathematical abilities. And what's interesting is he found that there are a number of solutions that come out of this equation. But one of the solutions is that there are three odd points. There are three odd points, L2, L1, and L3, where if you place an object at these locations, anything placed there will revolve around the sun at the same rate that the earth revolves about the sun. And that is, of course, the exact solution that the James Webb Telescope designers needed, because they didn't want to lose sight of the telescope. By having these two things move together in their orbit, they would always have direct line of sight to the telescope, and they could always communicate with it, and also receive images and data from the telescope.
Does
Now,
that mean they would be moving at the same speed, at the same rate?
they would be revolving around at the same rate. That's correct. So let's go back a moment to this previous thing. One way to think about why this works, and this is an approximation, it's actually more complicated than this. But basically, by having the satellite or the telescope located on the same line, the gravitational pull of the sun, which is affecting the satellite, can be added to the gravitational pull of the Earth on that satellite. So that the combination of the two, the gravitational pull of the sun and the gravitational pull of the Earth, together would be the same as if the satellite were located where the Earth is. And in that way, that's kind of a way of visualizing why an object placed here will revolve at the same rate around the sun as the Earth does. It's more complicated than this. It's actually quite a bit more complicated, but this is a good general view of why this works. So the James Webb Telescope designers decided, of course, to put the keep pushing the button. Decided to put the telescope at the L2 point. And these 3 points, which Euler had discovered, are called Lagrange Point 1, Lagrange Point 2, and Lagrange Point 3. Now you may be wondering, why are they called Lagrange points? I mean, shouldn't they be called, like I did, Euler points? After all, Euler's the one who discovered them. Who's this guy Lagrange? Well, Joseph Louis Lagrange was a mathematician who was also a very, very capable mathematician. He was an Italian-born scientist, but he moved early in his life to France, where he spent the rest of his life. And 10 years after Euler analyzed this problem, Lagrange decided to analyze it also. It's not clear whether Lagrange was aware of what Euler had done. There's nothing in the literature that tells us whether he knew about Euler's work or whether he didn't know about it. We just don't know. But whatever the situation was, he decided to analyze it. And of course, he was an excellent mathematician, and he came up with the same result that Euler did. Except that he realized there were 2 more points. There was the L4 point and L5 point located at 60-degree angles from the horizontal line. And so I'm not going to go into the explanation of why this works. It's fairly complicated. You have the sun is pulling down on the whatever's there in this direction. The Earth is pulling down in this direction. So you have a whole set of force vectors that you'd have to analyze. We don't need to go into that because we're really not going to be considering the L4 or L5 points. All we're interested in is the L2 point. So whatever you want to call it, whether you call it the Euler point or the Lagrange point, that's a great solution. So all you have to do is place the telescope at the L2 point and everything's solved, right? Well, unfortunately, there are complications. There are always complications. And the problem is that the L2 point is not stable. And one of the reasons it's not stable is because the Earth is revolving about the sun in an ellipse, not a circle. And that means that the distance of the Earth to the sun changes. There are times when the Earth is closer to the sun. There's times when the Earth is farther away from the sun. And that modifies this rather delicate balance between the gravitational pull of the sun and the gravitational pull of the Earth. The net effect of this means that L2 point
Satellite is.
Pardon?
That's a laser button.
Oh. There we go. This L2 point, oops. Let's get this right. This L2 point moves back and forth along this line. Now that's a problem, turns out. You can think of an object that's placed at the L2 point as being on the top of a gravitational hill. And so if the object that's placed there, for whatever reason, is displaced a little bit from the top of the hill, it'll begin falling down the hill one way or the other. It's actually a saddle rather than a hill, but for our purposes, we can think of it as a hill. So if it falls down the hill in this direction, it's moving toward the Earth. If it falls down the hill on the other side of this, it's falling away from the Earth, away from the Earth. And so as the L2 point moves back and forth, something might happen. If the L2 point moves away from the Earth, then the satellite will move down the hill in this direction toward the Earth. And that's fine because you'll be able to push the telescope back up into the L2 point anytime you wanted to. But if it moves in the other direction, if it moves over this hill on the other side, that's a major problem. And here's why. Here's a schematic of the James Webb Telescope. And the cold part of the telescope is the part we're not really talking about at all. But the hot side is where a couple of things are located, and that's what I like to point out. The one thing that we want to talk about is the thrusters or the jets that control the telescope and kind of tell it where to go and how to orient itself. That's located on the hot side. It's not located on the cold side because jets generate heat, and you don't want to generate heat on the cold side because you want your telescope to be sensitive to the infrared radiation. And while we won't get to it at the moment, keep in mind that the solar panel is also located in this area. So if the telescope falls over the other side of the hill, the only way you could bring it back toward the L2 point is to flip the telescope around, which you can do with the thrusters, and then point it back and fire the thrusters to push it back to where they want it to be. But that's a disaster, because when you point the thrusters so that they thrust the telescope back to the L2 point, it exposes the cold side to the full blast of the sun. And therefore, the cold side will begin to heat up. The cold side, the mirrors, and lots of the material there will begin to expand. There are glues and adhesives that are holding this whole thing together, and the glues and the adhesive would break. The telescope would basically become inoperable. So it's absolutely critical that the designers never, ever allow the telescope to go on the other side of that hill. So how do they do it? Well, what they decided to do is, instead of placing the telescope at the L2 point, they would place it at a position just in front of it. So in a way, it's going to be on the downside of the hill. It'll always be slowly slipping down the hill toward the Earth. But that's not a problem because they can fire off the thrusters to bring it back to the L2 point anytime it gets far enough out of the specification that they need. So the solution is there, right? That's all you have to do. Well, unfortunately, there's a complication. There's always a complication. And the complication in this case is that if you put the telescope here along this line, the telescope is always located in the shadow of the Earth. It's effectively in an eternal eclipse, which means that that solar panel, which is the only source of electricity for the telescope, will never get the full blast of the sun. And so it will never be able to generate enough electricity for the telescope to work properly. What to do? Well, there's only one thing you can do. You have to move the telescope from this point up out of the shadow of the Earth. And that's what they did. So,
Is that the L4 point?
pardon?
Is that the L4?
No, it's out actually still very close to the L2 point. Whoops. Hang on a second, I messed up here. I get these buttons right. So it's still the L2 point, it's just a little distance above it to get it out of the shadow. Now, this complicates things quite a bit, because now the force on the telescope is pointing in this direction toward the Earth. It's no longer pointing along this line. The same is true for the gravitational pull of the sun, but the sun is 94 million miles away from the telescope. So that angle is actually relatively small. You could pretty much ignore it. I think the designers actually take it into account when they're doing their computer modeling, but for our purposes, we can just assume that the gravitational pull of the sun is the same as it was when it was along this center line. But the gravitational pull of the Earth, which is much closer, that cannot be ignored. The force now is pulling in this direction, and we can kind of divide this up into two axes, called the x-axis in this direction and the y-axis in the vertical direction. And you can break this force up into two components. One is a component that pulls along in the same direction as the sun. That's the x component of this force. And then there's another component of the force which pulls it down back toward the center line. And that's the y component force. So what the designers do is they adjust this point a little bit because the telescope is a little bit farther from the Earth, and because the gravitational excuse me, attraction of the sun falls off as a square of the distance, you're going to have to increase or have to decrease the distance a little bit to make up for the increased distance that it's off because of this angle. But you can do it. And what they do is they choose a distance such that the x component of the PE's, the pull of the Earth, if you will, the pull of the Earth in the x direction, plus the pull of the Earth, pull of the sun combined together to give that magical number such that the telescope placed at this point will revolve about the sun at the same rate that the Earth does, just as if it would be pointed at the L2 point. But there's a problem. The y component is still here, and you can't ignore it. So left to its own devices, this y component will pull the telescope back down to the center point, and back into the shadow of the Earth. So you can't allow that to happen. And here's where they come up with an ingenious solution. What they would do is when they launch the telescope to the L2 point, they would launch it such that it comes up close to the L2 point. But as it comes up close to the L2 point, they would put it into an arc or a circle. And when it goes into an arc or a circle, there's generated what's called a centrifugal force. And the centrifugal force that they get from this will exactly equal, but it'd be in the opposite direction as the y component of this pull of the Earth. So the centrifugal force will offset this y component, and the telescope will never come back into the shadow. But the consequence of this is that the telescope is now going to be moving in an orbit around this point. And that's the final piece of the puzzle that they were able to solve. So here's the final configuration. Excuse me. You have the sun, the Earth. They actually have to take into account the moon. And actually, I believe they actually take into account the gravitational effect of Jupiter. But we're going to ignore all those details that they were actually have to take care of. You place the telescope near the L2 point. So the telescope revolves about this L2 point or near to the L2 point. And then this whole thing rotates. So it's a very complicated set of motion that's going on with the telescope. This is a little deceptive because this orbit is kind of showing as a circle. It's not really a circle at all. It's actually an ellipse. So fortunately, NASA has provided us with an animation which kind of really nicely illustrates what's going on here. So here's the Earth, here's the L2 point. And you can see they launched the satellite, the telescope from the Earth. It traveled for about a month to get to this point. And once it got to this point, they subjected with the thrusters on the telescope to put it into this kind of a loop. And when it went into that loop, it generated the centrifugal force, which then counteracted that Y component of the force that was trying to bring the telescope back down to the center point. And of course, it then goes into this orbit. And you can see that this is actually showing it all the way up to 2026 to show you. Now, this orbit is actually quite large.
Yeah.
The orbit at its closest point to the L2 point is about the distance of the Earth to the moon. So it's about 250,000 miles. It's actually a very large orbit. And in the farthest distance, it's about 3 times that. And they chose a large orbit for a very good reason. For much the same reason that planets far from the sun rotate around the sun more slowly than planets close to the sun. By making the orbit large, the telescope itself will be moving relatively slowly. It takes about 6 months for the telescope to make one complete orbit around the L2 point. And that's necessary because eventually they're going to take the telescope and try to point it at some particular object in space, some newborn star generated sometime close to the Big Bang. And they're going to want to stare at it for a long period of time. We do that on Earth by using telescopes that are put on mounts that are able to track the Earth. You can see this is going to be a considerably more complicated mount because it's actually moving in 2 directions simultaneously. But by putting it in that larger orbit, it moves slowly enough that they are able to compensate for the motion and be able to keep it fixed on any one point. I don't know if you could see it from there, but you can. There's this dot here on the L2 point. You can see it moving back and forth as the Earth moves in its orbit around the sun. And then the final slide shows the Earth.
Press it again, start
Press it again. Okay, yes. So here you have the sun located here. Here's the Earth. There's the L2 point. You can see the Earth and the L2 point are moving together. The telescope is moving around the L2 point. It then goes into this different perspective, but you can see it's a very complicated motion. Do I press it again? We start it again?
I think so. I have to go back first.
Okay, there it is. So once again, you can see how the Earth and the L2 point are moving together. The telescope is moving around this L2 point. And so they are able to constantly keep track of where the telescope is. They have always a line of sight and they're always able to control the telescope. I think it's a remarkable amount of engineering and science. And so the next time you're taking a look at the images coming from the James Webb Telescope, be amazed at the images, enjoy them greatly, but maybe tip your hat to the orbital scientists and the engineers that were able to design the system and actually pull it off. I mean, it's pretty amazing that they were able to transmit, to launch a satellite, their telescope into that thing, put it into such an orbit that would be able to be useful as an instrument. So give them a tip of the hat. Thank you for your attention.
All right, any questions?
Yeah, any questions if you have?
Yeah, I was gonna ask you about the moon. Kept thinking about, you mentioned that at the end.
That's just a little complication.
Yeah, it's a little complicated, and it does radiate some infrared radiation. It's not cold particularly. So it's another part of it that they've taken into account. But I believe that their actual modeling of this is much more complex than I've demonstrated here. I'm just giving you the kind of a broad outline of the way it works.
Yeah.
But it's pretty amazing, very amazing. So
Yeah, probably even taking into account the oblateness of the earth.
I think they even include that, that's correct. And of course, if we go back. Um, the distance, you can see a little bit discrepancy is different, slightly different orbits. That's because every so often they have to fire the thrusters to bring it back toward the L2 point, so that orbit varies a little bit. But that's also the reason that this telescope will only last for probably 15 years or so.
Without
Once,
fuel.
once the fuel runs out, there will be no way to pull that telescope back toward that L2 point. And at that point, it becomes at the mercy of the sun once again, and it will go around the sun at its own rate. They may decide to just push it away from the L2 point toward outer space or something. I don't know what they plan to do with it, but that would be the limitation of the telescope itself. What's remarkable is they didn't know how good they were going to be able to do this the first time they did this, and they nailed it the first time they did it. And so they actually saved an awful lot of fuel. The original specification was for the telescope to last 10 years, because they figured that with the fuel that they would expend getting it into this orbit would require that much fuel. By hitting it the first time, they now believe it might last 15 or 20 years. So,
What kind of fuel are they using?
I have no idea. Some
Probably
kind of
liquid
rocket fuel.
oxygen.
It's a problem. I don't know.
And then the solar power.
Oh, yeah, I would assume it was solar energy.
No, the solar energy is only the energy that powers the electricity. There's not enough power. I mean, it is kind of it does act like a sail, so that heat shield, which is very large, it's about the size of a tennis court. The sun's rays impinging on it does provide some pressure, and it does push the telescope, and that also has to be included in the calculations. But it's nowhere near enough to be able to orient the telescope and make it go into this kind of a loop here. You have to use the thrusters.
Since there's some other source of fuel.
Chemical.
There's some chemical fuel. I have no idea what it is.
Remember, you're pushing 14,000 pounds, right?
Right.
Oh, yeah.
Well, maybe 15, 20 years ago, just ask Elon Musk to fill it up on his way to Mars.
Yeah.
Let's always go further.
There you go.
Stop and deliver some more fuel.
Yeah,
You know, all the calculations. You know, I don't think of space as not, all these objects that attract each other and everything that causes forces, right? So I don't think of space as just zero anything. Like a meteor could go by or a new star could come into play and cause a shift
Mhm.
in all their calculations. They've assumed some sort of
yeah, no, there's a lot of,
environment with some
Lot
sort
of-
of.
micro meteors out there. I think they're
Could be anything.
small ones are hitting the panels or the mirror.
Yeah, I don't
That could
think
be a
they
real
hit,
issue.
well, they may hit the mirror, but the thing they were most concerned about was the heat shield.
You did a
And they
great
designed
job.
the heat shield so that it would withstand many hits from micrometeorites. But you're right, if I don't think anybody expects an asteroid or a
Yeah.
star to go floating by in the next 10
But it
years.
should.
It could, but
Yeah.
it's not
It's
likely.
pretty, in other words, it's a pretty steady environment.
It's a fairly steady environment.
Okay.
And almost all the objects you're thinking about, even though it's not an empty space, they're all immensely far away.
Far away.
I mean, the closest thing is the Earth at the moment, it's 1 million miles away.
Yeah.
So,
Not
all
the
these other
same,
things.
same gravitational forces were that it's actually accumulating in a lot of these smaller asteroids and things near the Lagrange point.
Uh-huh.
So it's sort of like vacuuming up, and so there's more small meteoroids near the Lagrange points than
Well, not
That's
near
it.
the L1, L2, or L3.
Oh, that's
They're unstable.
Yeah.
So anything that happens to get there is likely to be kicked off the far end of the hill and drift away.
Yeah.
Now, this is not true of the L4 and L5 points.
Right.
The L4 and L5 points are stable. And you might be wondering why they don't put the telescope there, because then you wouldn't have to expend any energy, any fuel. Well, the problem is, all this all this asteroids and stuff, if they happen to wander into that area, they're captured, they're stuck there. And so there's a lot of debris at the L4 and L5 points. And so it's not a good place to put a delicate telescope.
But because of that saddle type situation,
In
the other
in
one,
the
it's gonna
sat-
go
at the
one way
L4
or
and L-
another way and
the
drop
L-
out of.
Yeah.
At the
Drop
L4 and
into
L5
space.
points, there's no saddle, it's actually a valley. So you kind of fall into this valley and you can never get out. Well, you can if you move fast enough, or something are moving fast
It's like a force net. You know,
There
it's
you go.
just so interesting. And I can't even imagine how you put your presentation together and no notes, and you were able to stand up there and know it so well and
Yeah.
Yeah.
explain it so well. Thank you.
Yeah. Well, thank you, Jim. That was outstanding
All right.
presentation.
Thank you.
All right. Yeah, just, yeah, I wanted to give everybody a reminder that we do have, library where we loan books, and we have telescopes that people can borrow. And I just happen to have a C-Star S50 here tonight. If anybody, wants to borrow it and check it out, and now would be a good time to do it. So, I don't know if you're following on the internet, some of the remarkable images that people are getting, using the C-Star telescope. But it's there for our club members to use, so, yeah, keep that in mind.
Thanks for the reminder.
Okay, with that, I'll open it up to anybody who has any thoughts they want to talk about, or anything you'd like to see the club do in the future. I mean, this is your club. So you guys drive, what we do. Let's just get some ideas out there. No? Okay,
Cat Creek Observatory trip.
okay,
I'd like to focus on that a little more. It's
okay.
not just out there, but. I don't know.
Yeah, it's Thursday, they have self-guided tours, so, we go out there for our leisure. I think what we need to do as a club is people who want to go start putting in some candidate, Thursdays that they're available to go, and we could do the same thing as we did to the planetarium. We can carpool. I think it's about an hour drive from here, hour and a half.
Yeah, it's gotta be more than that.
Yeah, but not a whole lot. So,
What hours are they open or are they available?
it's on their website, but I think during the daytime they're, you can go out there, but yeah, we can definitely get some answers to that. But in the meantime, think about a Thursday that anybody who wants to go, kick out a date and propose it, and we'll get the word out and get a date selected. Okay, well, I'd like to thank everybody for coming. Everybody get out there and, look for Corona Borealis, see if you can see it, even with the moon. Because that nova is eventually gonna,
Is it gonna be green,
no, it won't be green.
red?
It's probably whitish to us. Yeah,
So will it just be like, there's no star and then all of a sudden we'll see a star?
Yep.
And we'll go, wow, that wasn't there before, now
Right.
it's here.
Yeah.
And it's as big as Polaris.
as bright as,
You could see the star.
well, with the
with a
telescope,
telescope.
you can see it because it's about 10th magnitude now. So you can actually see the star, but
Bigger.
not naked eye.
Okay.
But when you go out and look up, you'll see a star that wasn't there before.
We're zoned in on it on our star parade.
Yeah,
What's interesting, there's a lot of binary stars. In fact, there's probably, our single star, our sun, is probably not very common. Multiple systems predominate in the universe, and what I've always been fascinated though by these cannibalistic binaries, I call them, where one is pulling matter off of the other one. And,
It's
that
so
must be
dense.
Yeah.
actually be a planet around something.
Said
That, can you imagine what that must look,
Oh, yeah.
I can't even imagine what it would be like to, have that kind of thing up in the sky going on.
yeah. We actually live in a relatively friendly part of the universe compared to other places. So. All right, well, thank you, everybody.
Yeah, thank you. Thanks, Jim. Good job.